Hello, guys. I hope you're doing good. So here we have the double double circuit, and essentially, what double double is, it's a method used to convert binary numbers to BCD numbers. So essentially, a BCD number with binary coded decimal is basically like a number in which each digit is going to be is going to be represented using 4 bits. So I'm not really going to explain much about BCD because I'm just going to assume that you already know what it is if you're watching this video. And if you don't, please just look it up or something. So essentially, here I have um, two counters. So these two counters are going to be generating the binary input, and they're going to be counting from 0 to 255. However, since I only have two digits, I'm just going to be able to show numbers 0 to 99. Okay. And then this whole section right here, this is the actual double double circuit. Okay, and then I'm going to explain, in detail in a minute. And then here, these two guys right here are the 7447s, the BCD to 7 segment decoders. Okay, and then finally I have my displays. So let me just run it as I explain further, how the double double is implemented or is used. Okay. So essentially, so in the double double method, right? We mainly use shift registers, okay, which is sequential logic. So the way that they use shift registers is they, uh, you know, simply shift bits to the left, right? And whenever we're shifting these bits to the left, we're going to be checking the value stored in the shift register to see, you know, if uh, it meets a certain condition. So these are the conditions, right, for the algorithm to work. So if the value stored in the shift register is greater than or equal to 5, we add 3. Okay. However, if it's less than 5, we simply keep on shifting to the left, and we keep on repeating the same process until we no longer have any other remaining bits, and that's how we're able to generate the BCD you know the BCD number or the BCD output. So as you can tell, it's really hard for for us to implement this with shift registers if you don't have a microcontroller or some like I don't know, programmer IC. So if you're simply relying on hardcore digital electronics, it's going to be really hard for you to be able to implement this. That's why you see the circuit is really like you know large and complex. So essentially what these are simply multiplexers, right? These are 16 to 1 multiplexers. And the reason why I chose them, because it was a lot easier for me to implement the combinational logic um, using multiplexers. Okay. So essentially, as I was saying, we normally use sequential logic to implement the double dip. Okay, so now you see the output now is all wrong because we are now in the hundreds. So since the limit is only from 0 to 99, that means after 100, the output is going to be just showing, wrong information. Anyways, so um, as I was saying, since we normally use sequential logic to do this, probably with like a microcontroller for the control logic, because if you're using a shift register, you're going to need to send signals for like shifting, holding the value, parallel load, for example, if you want to perform an addition and updating the value. So it's a bit you know complicated for you to do that like without any microcontroller. you know so another way that you could do it is through combinational logic, but it's also hard as well, especially when you start dealing with um, data buses that are like larger bits, for example, like 8 bits. 8 bits. I think you probably need something like maybe I think 5 or 6 check bits. The circuit would really be much larger than this. So in this case, I only used 4 check bits, circuits. So what is a check bits circuit? So a check bits circuit basically, it gets an input of 4 bits, right? A number essentially, and then it checks to see if that number is, you know, greater than or equal to 5. So if it's greater than or equal to 5, it simply adds 3 to the number. But if it's, you know, less than 5, it simply, doesn't do anything to the number. Okay. So uh, to mimic how the shift register work, I had to use 4 of these, check bits, circuits. So one check bit circuit basically, had um, four 16 to 1 multiplexers. So if I zoom in here, let me see if I can zoom in. So let me just show you how this circuit looks, the complete, okay. So this is the check bits circuit. So as you can see, these are the selectors right here, A, B, C, D are the selectors. And then as you can see, we have 16 pins here. And then we have one output. And if you look at this sign here, it basically means, you know, there's an inversion going on. So that's why I had to use inverters here to get the actual output. Okay. So the reason why, I chose multiplexers again, it was a lot easier for me to implement, combinational logic, because as long as you know the SOP function, or like the SOP equation, you can easily, use multiplexers pretty much to mimic that equation or to mimic that function. Okay, I think if you've done like in digital electronics, you should be able to know, like, things about truth tables, K maps, and standard SOP functions. So SOP basically means sum of products. Okay, all right. So as I was saying, basically this is like a single check bits circuit, and it takes in 4 bits as input, and then it takes out 4 bits as well as output. Okay, so now let me uh, go deeper now into the combinational logic. So for that, I had a little diagram prepared for you guys. So let me just do this. Okay, so this is the truth table for the check bits circuit. Okay, so as you can see, A here, so A3 basically, that's like the MSB, and A0 that's going to be the LSB, as well as here X3 is the MSB, and the X0 is the what? Is the LSB. Okay, so A is the input, X is the output. Okay, so clearly, if you see, for example, the first case, I simply have 0. Since 0 is less than 5, the output is also going to be 0. But now that will change now when we have 5, because like I was saying, for the double double you know method or the algorithm, if the number is 5 or greater than 5, we need to add 3. So as you can see, if A is equal to 5, as you can see, this is 5 right here. That means if you add 3 to 5, you get what? You get 8, right? So 5 plus 3 is going to be 8. That's why you see the output is now what? It's now 8. So essentially, this is like the combination logic for the check bits circuit. So what I simply did now is that I used a 16 to 1 multiplexer for each output of X. So for example, X3 is going to have its own multiplexer, X3 has its own multiplexer, X1 has its own multiplexer, and X0 has its own multiplexer. And if you know the basics of, like, Boolean algebra, you can actually generate the SOP equation for each bit. It's like for each for example, for X0, I can generate its own SOP function, or its own SOP expression. Is the same way for X1, I can have another SOP equation. So with that now, I could easily implement 16 to 1 multiplexers. So yeah, essentially, that was how I was able to you know to know which connections should I, like, which pins should be 1 or 0 for the multiplexers. Okay, so now let's move on to the actual double circuit. So here we have the binary input, right? Binary input is there, and as you can see, these blocks here, they're representing the check bits circuit. And as I was saying, I needed 4 of these check bit circuit, and each check bit circuit has 4 16 to 1 multiplexers. So in total, I actually needed 16, um, 16 to 1 multiplexers. So, you can already see why the circuit was, really complex. And now imagine if you want to show like, you know, 3-digit numbers, that means you're probably going to need more of these check bits blocks. Okay, so you maybe need like 24 or 30 maybe, 16 to 1 multiplexers. So that's why it's a lot easier to implement using shift registers if you have a microcontroller. But if you don't have a microcontroller, it's going to be just as hard, but the design is going to be much more concise. Okay, so essentially here, as you can see, this is the MSB, right? This is the LSB. So essentially, it's going to be, initially it's going to take the first 4 bits of the number, right? And it checks to see if the number is, equal to 5 or, less than 5, like equal to 5 or greater than 5, or if it's, less than 5, okay? And then based on the output, basically, uh, you know, the MSB just goes straight to the output, and then the following 4 bits are now going to be inputted to another check bits circuit. So I think there's like a lot of videos which explain exactly what is going on here, because it's like it's a bit hard for you to like explain it, without like using visualizations. So if you really want to understand how the double circuit, like, algorithm works, I suggest maybe you can just search like double double method on YouTube, and I think that you find a lot of videos, actually explaining and showing you exactly what's going on. Because I feel like if I were to try to explain exactly what's going on here, I would need maybe like another video for me to do that. Okay, so essentially, this is like the circuit, and as you can see, here I'm going to have the BCD output, and after the BCD output, I'm just going to connect it to my encoders. Actually, they're supposed to be decoders, not encoders. Decoders and my displays. So um, essentially, that's the whole idea that's the whole idea, behind the double double circuit. And I actually noticed that on YouTube, there's like a lot of illustrations of how this method is used, like as in how it's implemented. But there's very there isn't much information on how to actually do a Proteus simulation for this, because best believe it's really hard. It's not easy. It's a lot easy maybe if you're using multiplexers, but imagine now if you're trying to use gates, it's pretty much close to impossible. So yeah, that's like the whole idea. And the reason why I made this video also as well, like someone made a request. They wanted to know how to implement this in Proteus. So yeah, that's the reason why I had to make a video. And in case if you guys maybe want me to implement the double table method with shift registers, without any microcontrollers, you should let me know in the comments. You know, if maybe if someone actually needs that, I might try to you know figure it out. I already have an idea, but I just need to make sure that you guys are interested enough to want to know more about the double table method. So yeah, that's basically it, guys. And let me just go back. Let me just go back. Let me just run the circuit one more time. Actually, just do this. No. Uh, okay. Okay, let's see if I can. Huh. Okay, so just one more time. Yeah. So what else did I wanna talk about? Oh yeah. Okay. So I wanted to also say something about the actual circuit. So as I was saying, it's each check bits block has four multiplexes. So for example, the first one is going to be right here. This is the first check bits circuit. The second one is going to be right here. And then the third one is going to be right here. And then I'm going to move on to the last one. Okay. So for example, as I was saying, if you want to show, say maybe 3 digits or 4 digits, I don't even know why you'd even want to do that. You're going to need a tremendous amount of these 16 to 1 multiplexers. And yeah, I feel like it's not really going to be practical because even right now, as you can see, the circuit itself is a bit complex to just show a display. It's not. It's actually more complex than my multiplier circuits or my multiplier multiply divider circuits, which sort of like perform maybe a much more useful function, you could say. So yeah, I just feel like if you really want to if you really want to show like larger numbers, maybe you try maybe to invest into using a microcontroller. Maybe it's going to be a lot easier for you. Or maybe if you could find a way you could implement shift registers, but it's going to be hella hard for you to to apply sequential logic where you need control logic and all of that. So yeah, so anyways guys, you know this is it, and I'll see you in the next one.